Okay, so let's continue morning session. So the next speaker is Elli Pomoni, who's going to tell us about hidden symmetries of 14 equals to gauge theories. Please, Elli.
Thank you very much. And let me begin by thanking the organizers. It's always a pleasure to come back. Yes. And sorry I didn't come last night. It was too much happiness. And this work. So this is what I will explain this paper. It is a bit esoteric for if you are not an integrable person, but I have made an explain it. So don't worry. Just stay with me, yes? Yes. So n equal to 4 is integrable in the planar limit. If you are not integrable, remember that we are only in the planar, yes? This is only large n, yes? And yes, using integrability, the spectral problem is solved, and you can use integrability to compute basically your favorite thing. This is amazing. And because I know that there are some students, the next 2 slides are only for them. So if you are super expert, you can chill. So Sibylle had in her talk the 3 things, the n equal to 4 super Young-Mills, ADS5 cross S5, and the spin chain. I will only have 2 for this talk. So what do we do? The important thing is that there is a one-to-one map, single trace operators to spin chain states. So this is a nice spin chain state, and here is a Feynman diagram, and you can see the insertion of the operator as a spin chain. So in some sense, the picture is enough. I will say a few more for the students. So the fields in n equal to 4 super Young-Mills are a representation of the color group, and because of that, it's important the order in which you put the fields when you make the operators. The way you should think is that operators are words, and every field in there is a letter. Yes? So, and what I said that they are non-abelian, the order matters. So what we do is we just did our letters, and the map is one-to-one. The moment we also impose that the spin chain has periodic boundary conditions, but not also translational invariance in order to capture the property of the trace. Yes? So that's the map, and that's a good exact map. And to make things very simple for this talk, I will only concentrate on the possible sector, subsector of things that I can look at, which is called the sector, which for n equal to 4 super Young-Mills is take 2 of the 3 complex scalars of the theory. They are rotated by SU2 symmetry. Here they want to spin up and down, and this SU2 is the symmetry of the spin chain. And most probably you studied this in your statistical mechanics course. And to correspondence, what we need to know is that the spectrum of operators is mapped to the energies of the spin chains. So in order to calculate that, we only need to calculate energies of the spin chain. So on the gauge theory side, with rotation operator, we have calculating Feynman diagrams, and this renormalization is mapped, is known by a Hamiltonian that acts on the spin chain. So the name of the game is to diagonalize this Hamiltonian. And this captures all these Feynman diagrams. And as an example for this SU2 sector, it so happens that after a concrete Feynman diagram calculation, you discover that this Hamiltonian is an XXX Hamiltonian, which is an integrable model, and everyone is very happy. Yes? So this is, in 2 slides for the students, what is the integrability for n equal to 4, at least the part I care about. Of course, there is way more and beautiful, and yeah. So now, great, n equal to 4 super Young-Mills is integrable, but you know, we are supposed to be physicists and we want to go to QCD eventually. Not quite yet, but the important question to answer is what happens for gauge theories as I reduce supersymmetry. Yes, this is a very important, honest question that we need to answer. So the next step after n equal to 4 super Young-Mills is n equal to 2 theories. And they have a, first of all, if you ask generically what is the landscape of n equal to 2 theories, it's basically vast and unknown, I would say. However, if you care about theories that have a Lagrangian description, Vasilis yesterday already said the word Lagrangian or non-Lagrangian. So only Lagrangian we know how to do integrability. Actually, the indication. So we know all the theories that are n equal to superconformal and have a Lagrangian description. And you can just look at them. And most of them are made by orbifolding n equal to 4 super Young-Mills. When I say the word orbifold, I have also orientifold here, so they are the same, more or less. Yeah? And originally deforming along the conformal manifold. So that's the name of the game. Orbifold marginal deformation. And for these things, we know well what the gravity dual is, so we can also have an ADS description for them. This is very important. And basically, all you do is you take the n equal to 4 paradigm, you orbifold, and then there is a B field that you need to play with, and that's your marginal deformation. You play with a B field. Yes?
Do you have an explicit Bernardo solution?
Yes, absolutely. It's in my first my PhD with Leonardo, the Veneziano limit. Yes. Yes, yes, yes. So the supergravity doesn't care about the B field because only H appears, and for us H is equal to 0.
How can the spectrum of the string depend on it?
Very good. String theory now becomes important. Supergravity is too simple. So the twisted states know about this. That's how it goes. Very good, yes. So, and what is also important is from the very beginning of the integrability, people discovered that at the orbifold point, which is the specific of the couplings, where all the couplings are equal, these theories are integrable. So very naively, all we need to do in this life to go beyond is we need to understand what the marginal deformation does to the spin chain. Simple, but yeah, let's go for it, yes? Let's try to understand, yes?
Before you go there, what about the theories that you do not obtain from orbifold?
Yeah, they are a little bit strange, and maybe you need to start from F theory to understand them. Some special crazy G2 blah blah. When I understand type 2B, I will go to F theory.
But are there examples maybe that are understood, or is it not understood?
What do you understand? So we know how to do string theory constructions. I think more or less, I mean, I wouldn't sign now a paper, but for more or less all, we know what is the gravity dual. You may have to do F theory to do that. Now integrability and all of these things, not even forget. Yeah. No, I think gravity dual to the right F theory person, they will tell you the most strange one, yeah. We can go, yeah. Good. Okay, maybe I will think just because you said Weil. So I will just say one thing. There are theories, I will say this later, but I say it already. There are theories like super QCD, n equal to QCD. What I tell you now, and you can ask me afterwards why Elli, is you should never study it by itself because this is too hard, because dual is a non-critical string, blah, blah, blah. You should always study an orbifold of which you can obtain this super QCD as a limit. Yes? So I just say that for now. Yeah? Great. So on the integrable model side, and here I want to insist and to try to brainwash all friends. Yes? So when you take a class in integrable models, they tell you there is rational, trigonometric, and elliptic. They teach you amazing things about the first two things, but then they start not telling you enough. And first of all, nobody even tells you that there are hyperelliptic examples. Find the strange papers by yourself. Yes? And so now let me stress something. So I already, for example, the XXX spin chain has U2 symmetry. So when people started in the old times, they started, for example, XXZ, and naively yourself, you naively say, oh, there is only U1. No, if you really do your calculations and you study, you discover that there is a bigger thing. There is NSU2, it's just an Elli group, it's a quantum group. And the same thing, and even more is here. Naively, you think that the XYZ model doesn't have a symmetry. However, it has an elliptic version of SU2. And actually, it's even very important how you choose your base, because there are different classifications of elliptic groups. So actually here, I would even say that there is a vast unexplored arena to play with. And also what is super bad is that the mathematicians and the physicists have not stopped talking at some point. And they know things that they don't know and the other way around. So even bridging this gap is like an important homework to do. Okay, now let's go back to theory. So we know n equal to 4 super young mills has SU4 R symmetry, n equal to 2 has SU2 cross U1, and n equal to 1 has only U1. But then you start studying spin chains and you start collecting evidences that something is happening. So already the beta deformed n equal to 1 is mentioned, and this has a quantum deformed SU4 R symmetry. Whether you like it or not, it's there. The most general to one marginal deformation that you can do has a 2-parameter deformation U4. So it's not as little as we thought. For the orbifolds, nobody talks about it, but if you read at the papers where they do the integrability stuff, they actually use U4, which why they do it, they shouldn't have done that. Yes? Never argue that an SU4 is there. SU4 is broken. And anyway, we had a very experimental paper where we started discovering that even away from the orbifold point, there is some type of deformation for. And in this talk, in some sense, I want to really go, what is that? Now, message, because I already said at the beginning, naively, we only need to understand the imaginations. So from all the examples that we know, of course, this is not a theorem. For examples, this is what you get, is that marginal deformations on the gauge theory side, it maps to quantum deformations of the symmetry algebra, yes. Yes, you have a bigger, this is the naive, no. Let's continue. Suzy algebra is for the beta deformed. The more the examples go down, it gets harder. But yes, that's where I am going in this life. Yes. So I think this is the important message that I want to, like, as far as we know, marginal deformations, they correspond to quantum deformation of SU4. By the way, all of the theories that we know how to study with integrability, all of them, they are a very close daughter to n equal to 4. So you can say it's an accident that this works so nicely, but anyway, that's what we have. And now what I want to really understand is what is the effect of the orbifolding on the spin chain. Yes? So let's do this. So this will be my prime example. Like, do the simplest possible n equal to 2 theory that you obtain as an and then marginal deformation. Okay, usually in the 10D, in the type 2B strings, you do this orbifold. In the gauge theory side, this is not enough. You need to remember that there are Champatton labels, so you also need to do the orbifold at the color indices of your and this is what happens in the end of the orbifolding procedure. Maybe just stress the difference with n equal to 4 is that you have fields in the adjoint representation of the one color group and the other, but you also have bifundamentals. And this makes all the difference when it comes to integrability. Yes? This theory is enough to understand all the novel features that I want to understand. And what I try to say for the is super QCD, you should never try to understand it alone. You should do it as a limit of this theory. Now we start. So n equal to 4 super young mills is very nice because all the fields are in the adjoint representation. The superconductor algebra has a unique singleton representation. So the way Hilbert space is like crossing putting however you like the fields on your speed chain, and you win. Now, the moment you go down to n equal to 2, generically, and there is no way out, you have to deal with this in this life, is that there are distinct ultra-short representations of this algebra. One is built upon the vector multiplet, and one is built upon the higher multiplet. And the vector is always in the adjoint, and the hyper is fundamental. That's extremely important. Now what happens? You cannot just put the fields, the however you like in the word, because if you want to be in the largen limit, you always contract, and I have chosen my conventions so that you can immediately see how you act. So these are the color indices. You have to have a 2, follow it by a 2. This is not allowed. This would be sort of making a double trace operator if you do that. So the fact that not goes has been the biggest contamination, at least of my thought, but I think of any person that has tried to think about this problem. And now I have two ways to think about it, which I think are fantastic. So the one is a more physicsy way, but that's already something that people don't think every day. You need to think about a so-called dynamical spin chain. So what is the simplest way to think about what is this word? And this is not the Bizert dynamical for the integrable people, it's some other dynamical. So begin with an n equal to 4 mother operator. You should always think about sons and daughters, yes. And after the or before, you always get, after following the projection that I try to explain here, you get two operators. And as long as you specify the very first index, you know the rest follows. So this is what is dynamical about it, like when you solve a differential equation, you have a condition and then you solve. That's what's dynamical about it. So that's one way to think about it, and it's a very good way. But actually in this paper that I'm describing now, we found a better way, and this is very important because if you ever want to make contact with the mathematical literature, you have to follow the way they think. And the modern mathematicians think in category theory. And the simplest object they have is called groupoid. But we know what is a path groupoid. We don't need to learn math. It's basically take your quiver and follow the arrows. That's a path groupoid. So the way to understand Hilbert space of spin chains is through this path groupoid. Follow the arrow. And this captures clearly, obviously for us, the correct Hilbert space. But it's another mathematical object. Now, there is not only the path groupoid which describes the Hilbert space. There is another groupoid that I will now try to explain. Explains to you why this as U4 is there. It's not Elli algebra as U4. It's something that I will call the R-symmetry algebroid. Let's go for it. So, what do we learn in school? We learn, we have two fields, the tablet of SU2, this is good for n equal to 4, no problem. Now, for n equal to 2 theories after the orbifold, and this is what you learn when you take the standard symmetry class, naively you would put these guys together in one doublet, but that's not allowed because you are never allowed to put apples and oranges, yes? So this is in the adjoint, this is the bifundamental, they don't belong together. So I need to make a new construction which will take into account, and that's precisely by abandoning the Elli algebra and going to Elli algebroid. By the way, I am not going to be careful in this talk what is groupoid algebroid. I'm thinking if you only group Elli algebra, you do the same and you are fine. Yeah? Now, what is happening? So for normal SU2 Lie groups, we have a raising and a lowering operator that will go up and down with your spins or your two fields. When you have lost this guy, you can say, let's start, like play stupid, it pays to be stupid, and just postulate generators that do the same thing, yeah? Clearly, operators, they are not just normal Lie algebra operators, they also know about the color, the representations of the color group, or better, they know about the Z2 of the orbifold. Now, this is, if you want to know what is algebroid, here you go. I mean, with the next few slides. So, at the level of single words, and I will tell you later what to do with more letters, all you need to do is to say, yes, my 4 different fields, they don't live in the vector. So I have a set of 4 different types of vector spaces. And I have this action, so the arrows, so the action of the generators of the algebroid. That's what it is. And in our case, because we are doing a Z2 orbifold, but you can clearly imagine how to generalize this very easily, there is another operation that takes things from up here to down here. It changes the index 1 to 2. And here the same. So this takes into account the orbifold. So I am now defining something that knows about the SU2, but it also knows about the Z2. And the set on which it acts is 4 different elements. If you know category theory, this is a small category. But forget about it. Now, 1 letter was too easy. Now the real deal comes the moment you want to have at least 2 letters. N equal to 4 super young mills with this nice SU2R symmetry. We do how we learn when we add spins in quantum mechanics. This is the product, the way to put 2 sides together. You either act on the one or the other with no factors, no nothing. And that's how you build from a up-up spin and up and down symmetrized. So this is part of the triplet of SU2, yeah? Now you naively find some sigmas. You want to do the same, yes? So you go this naive and you act and you get foul, not allowed. So this color contraction is not allowed. Now it becomes that we are in this algebroid picture and we have a new friend, the gamma, the guy that tells us how to go up and down. So if you realize your coproduct by adding this baby, and this is not some crazy thing that I wrote. This exists in math. It's called, anyway, it exists. I'm not going to tell crazy names. So you take this, you act, and you win. It's allowed. Yes? And you can continue. You can choose however many letters in your word. Whenever you had a broken generator that would make a mess, you put gammas. If you will put things on the right or on the left is a convention, but I have chosen one and right. So you put gammas all here, and this guy acts properly, and it raises you up and down, and you can make all your representation. It's beautiful. Yeah. Gamma, here is the definition. So it acts by changing the color from 1 to 2. Yes? So it's the non-trivial element of Z2 that squares to 1. And yeah, here the same. So this is what this is. And these generators now, since you can say that they obey like the SU2 algebra, of course this is not the SU2 algebra. It's because you need to have also all of this decoration indices that know about the color. And I am writing this, you can take this and do another orbifold, now this equation. Yes? Yes. So there is a paper by Diagraph that does this for minimal models. More after the talk. Yes. And then you can very clearly embed this construction. Opala. You can embed this construction as U4R symmetry. I am not going to bother you now with the group theory, but you can do it. It's the same thing. This is what is now the groupoid or the algebroid. So you have, for any length now, that's why I call it V. You can have open strings that they end in the same brain, open strings that they end in the others. and so on. So 4 of them, and you have all the possible actions of all the different broken or unbroken generators. Unbroken generators, you don't mess with the coproduct, you keep it how we learn in the quantics. Broken, you put your gammas. And then you can check they obey SU4, of course with this decoration. Now, if this was it, I would not be giving a talk. What we will do now is the Lagrangian, and we will show that it's invariant under this strange thing. And I only know how to do this in the large N because I need to have this words making task. Yeah? So, first of all, trace operators are nice, but they have this periodicity thing. And usually when you do all of this more integrable stuff, you want to just act. If you have a nearest neighbor Hamiltonian, you want to act on 2 sides to ignore the rest. So usually you cut open the chains and you think about open chains. So I'm going to do this. You don't have to do this, and maybe this is something that I am constantly debating with myself. Maybe it makes life harder to always cut, because in gauge theory this makes gauge non-invariant operators. But anyway, I will cut. Prescription for how to cut when you have an operator with a trace, and it's this cyclic prescription. Yes, so that's how I cut. Okay, the one I drop in the next slides. And this will be enough to show you Lagrangian is invariant under this SU4 Z2 algebroid. So let's do it. And to not kill you, I will only show you how to do the superpotential, which is the most non-trivial thing you have to do. Everything else is easy. So this is my superpotential first at the orbifold point where the 2 couplings are equal. I cut it first by doing what I said before. And I pull out the 1 over G because who cares about it? And act, this is just an example with a sigma plus. And I made also colors. Okay, they're not all of them super visible, but you get a cancellation. So this guy that was not supposed to be there gives a 0 when I act on my superpotential. You can do the same thing for the Kähler part, or you can torture. I tortured my PhD student by making him go also to components and check everything in components. And in components it's harder because you have the scalar potential, which is 4 sides. So clearly there's more to check. So, but you can go through all the pain and you can test all of it, and you get that the Lagrangian is invariant. And if you do not open chain language that I'm talking about now, because the Lagrangian is a trace, you are doing this in the equations of motion. Yes? Great. So now we have shown that the orbifold is good and they have SU4, because not they have an SU4 Lie. They have an SU4 Lie algebroid based on the Z2. That's the correct way to think about them. Yes, the large limit plays a role in the thinking of things about like the spin chain language. No, but no. What I am doing is very important. I have sites that I can name 1, 2, 3, and I can put my fields on them and find a coproduct. So this type of thing that I am defining, this type of things, if there is no spin chain, it doesn't exist. So the independent statement is in Zen limit, when you are allowed to use this machinery, I can check it's invariant. That's the only statement. Yes, if you wish, what I haven't checked, because I'm not allowed even to think about checking them, is the double trace, guys. Naively in the superpotential, there is no double trace. To components, there are also double traces, and if you knew to write this formalism, you would also check that. Yeah. What does it mean? basically, yes, what is not known is this. I mean, maybe Charlotte has worked, so you try to do in N, and it was, I don't know, like, yeah, I really don't know. Maybe we can talk after, but I really don't know how to go beyond this formalism. So, good, we checked the invariance at the orbifold point. Now we want to check it away from the orbifold point. And in order to do that, I need to, good, here we are. So we want to go away from the orbifold point. I define kappa as the ratio of two couplings. And I am going to show you that the deformation is captured by a Drinfeld-like twist. And I call it Drinfeld-like because I don't understand the mathematicians that they talk about groupoids. I only understand the simpler ones. So it's something like Drinfeld, but I don't know if all the, someone needs to make sure that it's all the yeah, anyway, it doesn't matter, it's what it is. And where do you get this twist? This guy, you get it by at the F and the D terms. So this is the F term without the marginal deformation. This is one, I just show one of them, yeah? And you really want to have, now that you have this marginal deformation, so you, if you calculate an operator at the spin chain level that does this job. And this we had already hinted in the previous paper. Great. I want to give a little bit of intuition from because this is very important. That's the only string theory slide. So first of all, the F terms, if you forget about this, what they capture is the planes that are transverse to the D when I'm looking at the scalars. Yes, this is the F and the D terms, this is what they do for you. So when kappa is equal to 0, they show you that there is an SO6 symmetry and everything is nice. And once you have these kappas, or whatever other deformation, this is the same for the beta deformed, for everything, it basically tells you that the transverse directions to the D3 branes are somehow deformed, squashed. But this we know. And we know since a very, very, very long time. So what this guy said is that once there is a B field that is transverse to the D3 brane, precisely what we have, the open strings, which are these guys, they see non-commutative geometry. And in the spin chain language, it's basically what we call a quantum plane. Important.
Again, so if I take these the form background away from the orbital point, like the Green-Schwarz action for closed strings.
Nobody has written this yet.
Right, that was I get my question.
Nobody has written this yet.
But I thought you said that the background is known. So what's
the background is a geometry. The background is not a Green-Schwarz action. Who cares the specific? The background is a metric, a B field, blah, blah, blah. And the background is given by string theory.
And that is known or not known?
It's known.
As to what is the problem there?
The problem is that someone, so from the string theory side, what is not done yet, I'm trying to convince people, is that we need to write down the Green-Schwarz action and calculate. Yes, it is written, but then you need to calculate. Let's not, we are really...
Is more general.
Yes.
Such a, if this is the only deformation that you have,
yes.
I don't see how close strings would couple.
Yes, because you are used to untwisted models, and twisted models have twisted strings, and twisted strings directly couple to the B field. That's how they couple. And if you do RNS formally, you can directly show that to make sure you have wall-sheet supersymmetry, you basically change boundary condition. This is a calculation that you can do that I know how to do, and you can put the B field in the way you define your boundary conditions. So that's how it works. But yes, we need to, I commit to bring this in a form that the integrability people like, and then they can take it and do whatever they want with it. Yet. Good. Now we stay to the spin chain again. And we define our twist the way I said. When you have this mathematical object, it's the same like in your talk. That's how you define now a deformed coproduct, the deformed way these generators act. There is here a kappa, this is a marginal deformation, to some operator S. The operator S is the operator that asks the field, what is your first index? And it gives only 1 and -1 depending on what the first index is. And it commutes with this way. So we know everything. And now we do the same again. Here is the superpotential with G1 not equal to each other. Open up. There is something here in blue. I try to put color so that you can follow with your eyes. The coproduct, this is the same calculation as before. Kappas cancel. And then you get 0 the same way. That's how it works. And Kähler, the same. Ah, very nice. Good. So I have shown up to now that if you use the spin chain formalism and you define your coproduct the way I did, you can show that the Lagrangian is invariant under this symmetry. Yes, this is the equivalent for the integrable people of the Bizert papers showing that, when he wanted to show the Youngian. So I just showed the before there, but as in this groupoid sense. So that's done. Now, that's not just that. You can also go ahead and study now the spectrum. At this moment, I don't care about energies, calculating energies. But what I care is about representation theory of this groupoid. What is that? So what I can is that I can make representations of this algebraic structure. And this is how we do it. First, I start with a simple possible SU2. And I start, you can do at any length, no fear, no problem. Spin up, spin down. Acting with this coproduct, you can go up and down, and you can make this multiplet completely. This you are not supposed to be doing. Yes, nobody should allow this. Only you can do this. You get sprinkled kappas everywhere in place. And these kappas are the correct kappas that when I was a student and Leonardo made me calculate all the Feynman diagrams, is the same kappas. And this is a highly non-trivial test that this thing works. Yes? So this agrees with either, you can say, direct diagonalization of the Hamiltonian or Feynman diagrams. And also for the people that care about n equal to 2 theories in general, this multiplet now has Higgs branch type of operators, Coulomb branch type of operators, and mixed branch operators, all in one multiplet. So this is not important only for the integrability business. This should eventually show up when we learn to do BPS counting, all the Nekrasov partition functions, all of this should know about these things. So this implies a relation between Schur and Coulomb branch index. Yeah, I don't know. So there is a lot. Just only in the infinite, but still. So there is like a tone of modern developments that they should know about. The chiral algebras should know about the chiral ring of the tone.
So this is for a specific multiplet, right?
Yes. Yes. Yes.
You give me any multiplet, so I get any multiplet in the spectrum?
Yes. Wait. Yeah. I will tell you the truth. So, first of all, for the SU, it's very easy to do this game. Yes, because the coproduct is very simple. What I have not shown in this slide, because this is very baroque, is what is in this slide. What you need to do when you embed everything in the SU4, is the difficulty there, and this makes things. I don't know how to think about it in the correct way to phrase the computer. Vasilis yesterday in the talk, he was saying how you should talk to the AI so that in a way that it understands. I don't even know how to talk to myself to make this problem nice yet. So the moment you embed everything in SU4, you also have the quantum plane relations that have to do with the D terms that capture the reality condition, the fact that you have SO6. So this is super hard, and now I can only efficiently do it for 2 sites. So in 2 sites, for the full SU4 or SO, the 20 prime, the 15, and the 1. The 1 is trivially, there is nothing there to do. Here is the 20 prime, and here is the 15. And what I don't show you the calculation because this is still hard. You can go around with, so in this, I have these arrows. So these arrows, on the green, are the ones that we know that they are there and they are unbroken and they should be there. But there are also all the blue arrows. And the blue have not been there, yeah? And you make this multiplet, and then you can actually check it also against, you can say time or spin chain diagonalization, and you can do the same with, and you can also get it, yeah? So this is, how should I say? If I had tried to do, actually I tried to do 3, but my PhD student wanted to kill me. So there is, I need to think how to make this efficient, yes. So this is the state of the art. Good, so here is a conjecture. Now I'm wrapping up. So I think that what I explained here can be done for any theory with less supersymmetry than n equal to 4, which you can make it an orbifold or an orientifold, yes? So you really just do the orbifold or the orientifold, and then you marginally deform. And it should, the construction should go identical. The SU4 algebroid should just be there. And then because I only used, by the way, I am insisting in this, I only used n equal to 1 language to do this calculation. So it's not something that should be special about n equal to 2 theories. And this I haven't done, but I also cannot see how not going to the whole thing, you know, I don't see the obstruction, okay, without having done the calculation. And what is important, the important message is that broken generators are upgraded algebroid structure. And from string theory, this really makes, and this is really this, like this digraph paper. Now, what do we have? We have naively broken generators due to the orbifold. They come back in the groupoid. The marginal is captured by a Drinfeld twist. The is invariant, and the spectrum, to the degree we can check, lives in representations of this new structure. Currently, I have a master student doing general ZK orbifolds, and everything seems to follow. We want to do more multiplets, but I need to think about it in a better way. I think is that I clearly don't understand how to use algebroids. And yeah, compare. And then this is also a homework. Now, I said this already, and this is very important. This should play a role for BPS counting. Like indices or Nekrasov or whoever you like, this should be there. Yeah, anyway. So, and again, I think that this were more general. Now, there is this paper. This paper changed a little bit my life when I read it, because when I was reading the older paper, I was not quite understanding at all, basically. Not quite. I was not understanding at all the groupoid sections. But with this paper, I was able to see that he has a Baroque way of talking, but it's the same with me. So his path, a very funny way of talking things, is my path groupoid. It's all the same. You just follow those. And this is really in this paper. This is a very new paper, and I had never read it. And there is another, okay, I will maybe say in the next slide the word. Something else that is very cool, because I have never seen this in physics. There is actually a two category. So groupoids, the ones that I described, are one categories. They combine into a two category. Trivially, you follow the arrows, and I am really wondering what the implications of that is. There has to be, at DEGI we have these super categorical people, and they immediately write down braiding and stuff if you tell them the category. So I am like, this is my hope now, that my two category will do the job. I don't know. And this is a more broad, so this slide is not only about this paper, it's the more broad thing. So what we have nailed in the past is coordinate best with all the pain that it takes, and there are this one published already, one coming, heroic papers. My student Denise has led. I cannot tell you what she did, but we did 3 magnons and 4 magnons in a specific vacuum. N equal to 2 spin chains have actually vacuum, and there are 2 different ones, and physics looks very different around the different vacuum. And it looks like, even though before in the past when I was a student, we thought that the Young-Baxter is not satisfied and the system is not integrable, it seems completely wrong, because if you think in the dynamical, what you need to do is you write here your R matrix. You go to the green, you need to write the green R matrix. And when you go to the whatever is this color, you need to write that R matrix. So following this logic, there is a new type of Young-Baxter that is actually, and if you really look the way things worked in this paper, basically we were flipping the rapidity of the scattering so that actually we basically make the Young-Baxter come back. Of course, there was a pace to pray. You can ask me questions if you want. Yeah, anyway. And then there is another thing that is happening right now, which is very beautiful. Now that we understand all of this, we are finding that they are higher charges. And they are very cool because you start with, you have a bunch of states with this energy. First, you find that this higher charge exists, and then you act with this guy on this same energy, and it splits them. And usually what happens is that you split, and maybe there is still some energies equal after a Q3 acted, and then you act with a Q5, and then they further split. So there is something going on that is very beautiful, that I don't understand, but it's experimental now, but something exists. Yes? Yes, and with this, thank you. Ευχαριστώ for the Greek organizers.